Hi friends, welcome back to Edupedia world. Last lecture we discussed in details the different electromagnetic radiations. Today we will switch to a new topic, which is the last topic on light. This is known as scattering. We'll understand what scattering is, the basic understanding behind it, and we'll see specifically the concept of scattering at the blue end of visible light and the red end of the visible light, and what is the difference caused by the wavelength. Finally, we will see some real life examples where scattering takes place, and it will be an interesting discussion. So let's begin studying scattering. In our day-to-day life, you must have encountered or seen many a times a situation where the ray of light entering through the window is scattered by the dust particles, and that helps you see the whole beam of light, how the sunlight is entering the room. Right, so that is what the scattering of light is. The dust particles scatter the light. As a result, you can see the exact path followed by the light. Now, the scattering of light in general takes place in the Earth's atmosphere by dust particles and the air molecules. Those things scatter the ray of light. Now, formally, the scattering can be defined as the process of absorption and re-emission of the wavelength. Absorption and re-emission of the light. Okay. Now, this phenomena of absorption and re-emission of the light takes place by the dust and air molecules present, and how much absorption and emission takes place depends on what is the size of the particles with respect to the wavelength. So normally scattering will take place only when the size of particle, that is dust particle or air molecules, is smaller than the wavelength. Okay. Now, a scientist who goes by the name of Rayleigh discovered this phenomena, or he studied this phenomena, and found that the scattering, the intensity of scattered light is proportional to inverse of fourth power of the wavelength. What does this mean? This means that wavelength, the larger the wavelength, the less is the scattering, and smaller the wavelength, more is the scattering. Now we know that the range of visible light is from 4000 angstrom to 8000 angstrom. 4000 angstrom is violet, 8000 angstrom is red. So given that the intensity of scattered light is inversely proportional to the fourth power of wavelength, this being the smallest will be scattered the maximum. So max scattering, and this is minimum scattering. Therefore, what we can conclude from this is if the size of the particle is smaller than the wavelength, then the violet light will be scattered the most and the red light will be scattered the least. And as a result, this has some practical implications. We will discuss those implications in a while, but before that I want to point out another aspect, that given that the size of the particle is larger than the wavelength, then all the wavelengths will be scattered to the same extent. So let me write it down. For large particles, by large particle I mean larger than the wavelength, the extent of scattering is similar. So basically this phenomena, the 1 upon lambda to power 4, will not come into picture, but this comes into picture for very fine dust particles or air molecules. Okay, now with this background, let us see some of the practical situations where this affects us, or where it plays a role. You must have observed that during sunrise and sunset, the sky appears reddish in color, right? Now, why is that? Why is that during sunset or sunrise it appears reddish? Let's imagine we have our earth here. Now during sunrise or sunset, normally the sun will be close to the horizon, right? It will be close to the horizons. Imagining you are sitting somewhere here, so the light will have to travel a large atmosphere, part of the atmosphere. Suppose the atmosphere is something like this. So if it were direct, if the rays were going to come directly, then it would have come like this, a less distance to be traveled. But since at sunrise and sunset it is close to the horizon, more distance needs to be traveled. Now as a result of that, what happens? The extent of scattering that can take place is more, because obviously more distance is available for scattering to take place, since there is more length of atmosphere available. Now what will happen is that the blue or the violet side of the visible light, let's tell it blue, will scatter more, and red will scatter less. Therefore what will happen? Less blue will be visible to us. Blue will go away in different directions, whereas red will kind of mostly come through. As a result, we will see red, right? Therefore sky will appear reddish or orangish during early morning and during sunset, during sunrise or sunset. So this is one of the practical phenomena where you observe scattering. Second is, if you consider the case when during noon, what will happen? During noon the sun will be overhead, right? So the ray of light has to travel through a very thin layer of atmosphere compared to during sunrise or sunset. Therefore the extent of scattering will be much less. The extent of scattering will be less during midday. This is midday. Given that the extent of scattering will be less during midday, the effective scattering of blue or violet will be not very different from that of red, right? Therefore, the sky will appear mostly, or the sun directly above will appear mostly whitish in color, right? Let me write it here. During day, sun appears white, and this is also mainly during sunrise or sunset. Mainly the sun and the surrounding area of the sun will appear reddish, not the sky, not the whole sky, I mean. Okay, so this is one phenomena during sunrise and sunset. This is phenomena during the midday. Let me write midday. Okay, now a third phenomena that can be explained using the scattering phenomena is that the sky appears blue to us, right? But suppose you were to go to moon where there is no atmosphere. You know how the sky will appear. The sky will appear pitch black even when sun is at the peak. The reason is the absence of atmosphere results in zero scattering in the moon. And because of absence of scattering, the sky appears black. Let me explain it from Earth's perspective. See, in this Earth, what is happening, that throughout the day the blue is getting scattered more or less, right? Now blue is scattered, and this scattered blue keeps on let me use blue color. This scattered blue keeps on striking particles, and ultimately it ends up meeting your eye, and it appears as if the blue light is coming through the different parts of the sky, not the sun, different parts of the sky. As a result, given that blue has maximum scattering, we observe the sky to be blue. Sky appears blue. Since blue scatters the most. When I say blue scatters the most, it includes the range that is blue and violet, indigo. So you can understand that. But the bottom line is sky appears bluish because of the scattering, and blue being the most prominent color being scattered, it appears that from the other parts of the sky actually blue light is coming, which is not possible in the case of the moon. Since there is absence of atmosphere, what happens is from other parts of the sky, if this were the moon, there is no scattering, the sunlight is directly coming into your eye, there is no scattering, hence rest of the sky appears pitch black. Okay, so this is also the result that sky appears black in space, or in general in absence of an atmosphere. Okay, so you have seen many practical situations where the phenomena of scattering affects us, like the reddish sun during sunrise and sunset, the whitish sun during the midday, the appearance of blue for the sky, and if you were to go to space, the sky appearing black, all these things. Okay, with this I will close the lesson on scattering, and this was the last topic on light. We have finished the chapter on light. Next we will discuss sound. Till then, have a great day. Goodbye.